thanks to you for the introduction, and good afternoon also from my side. Yeah, so we heard a lot about ocean atmosphere coupling. So now I'm also going to the land atmosphere coupling on our work at ECMWF at the moment. So I want to give credit to my colleagues and that have been working with me from the DA methodology team and the coupled assimilation team. And what I'm basically talking about today is coupled DA. Wanted to first start with like why are we doing coupled DA and what are the advantages with it, and then I come to our land data simulation system at ECMWF because we need to know about the land system before we can couple it, and the focus of this talk will be on exploring outer loop land atmosphere DA. So there had been a lot of infrastructural developments in our IFS, and this is pretty much still a work in progress. So the aim was to find an optimal degree of coupling. I'm gonna come to that in a minute, what I mean with that, and then I'm gonna show you some results about like how this coupling configurations, so different coupling configurations were assessed and evaluated in terms of their atmospheric impact. And then, so the idea is if we have an enhanced coupling possibility, we can make use of interface observations and certain frameworks we are developing at ECMWF, which I'm explaining as well. So first, starting off with coupled DA. So we're running a coupled model at ECMWF. So we have the fluxes, which kind of take the X or give us the exchange between the land and the atmosphere. But yeah, we have a different methods of how to couple the DA systems. And so the idea is we want to have an enhanced consistency between two or more Earth system components because we want to exchange information between them. So usually in DA, we want to maximize the use of our high quality observations and don't want to throw away a lot of them. So basically the idea will be to have a better exploitation of observations which are sensitive or which have a certain information content to more than one Earth system component rather than filtering them out. And the project I'm working in is called Ceres. And Ceres is focusing on land atmosphere coupled DA. And so there is a different working package, and one of them is looking at unifying our current land system to make it suitable for this activities of outer loop land atmosphere coupling. And then the second step, having this land atmosphere coupling in place. And this is what I'm going to be focusing on here. And the idea is to use this because it's the more you couple the land with the atmosphere, the more information you give to the land and vice versa to the atmosphere. So this methodology has to be proven. There is a good example to how to prove it would be like to look at the global reanalysis and also like to initialize longer runs, like seasonal forecasts from it. So if I make huge changes to the land or the atmosphere, it's good to test it in longer runs. So what are the types of coupled data simulation? I think most of you are familiar with that, but I'll just repeat it. It is, so the weakly coupled system would be that I have separate Earth system components. So in all of these components, they do the analysis separately. So different DA approaches, for example. And then this initial conditions or the update is then coupled through cycling. So I share the initial conditions between consecutive DA windows. And then on the other side, we have a strong or a fully coupled system. So that means we have all the variables, land and atmosphere in this case, in the same control vector, and we have a joint analysis where we update all of them at the same time. And now what I'm talking about is a quasi-strongly coupled system. So we have still separate DA systems, but we can balance our initial or our updated conditions within the DA window. So basically, we talk about outer loop coupling, the way the 40VAR works. We have different outer loops, and then we can feed back within these outer loops the atmospheric and the land surface fields. So we have the benefit of in each outer loop to have the most updated system. And just give you an idea about our kind of strategy at ESMWF, our future generation Era 7 system that ideally would look like, or this is planned to look like the following, like that we have the different outer loops. So we're cycling through the analysis here for the 40 var, which is already in place, but also having the NEMO var, which is in the next in WP cycle present, and then also having the green box here. You see it's a land data assimilation system also within this outer loop coupled scenario. But just looking at where we are, so our land data assimilation system of the current operational cycle at ESMWF, so it has a certain amount of observations and different, so it's a myriad of different data assimilation approaches in order to get the updates for our control variables, which is like soil moisture, soil temperature, snow depth, so on. And I want to just give you, for those who are not familiar with, so we have a kind of a pre-analysis system here, which is the two-dimensional optimal interpolation, where we use the in situ 2-meter temperature relative humidity observations and produce a gridded version, which we call the pseudo observations. And these ones are then assimilated into our land data assimilation system, into our, for example, our simplified extended control vector to produce soil moisture, or here the one-dimensional optimal interpolation to produce soil temperature and snow temperature. And the future, or the aim is to have a unified system based on our most advanced simplified extended Kalman filter, because this method is based on the ensemble of data simulation. So the sensitivities between the atmosphere and the land are based on the spread we have in our EDA. So just another kind of image, what I just showed, like this land data simulation system. You see the different DA approaches, and where we come from at the moment, we have only in this simplified extended Kalman filter control vector the soil moisture 3 layers. And the first step was to kind of successively get rid of the other DA approaches and put the control variables together with the ones we have already in the SEKF. And the first step was here towards a unified system to have the soil and snow temperature in the SEKF. And why is that important? So this basically, so soil moisture acts on a larger temporal scale, while the soil temperature, especially at the top layer, has a strong diurnal cycle. And once we want to go to outer loop coupling, we would like to have these variables in the control vector, because they might be the most sensitive ones and the ones we can most kind of elaborate. So this is this enhanced consistency already in the land data simulation system is kind of prerequisite to enable the outer loop land atmosphere coupling. So just give you an idea how the weakly coupled system looks like we are at the moment at. So we're running the SEKF essentially in parallel to the 40 var. We have separate quality trajectories, which is the coupled model. And this is a very busy graph here, but I just wanted to get you focused here what's happening here. So we have the atmospheric assimilation, which is 40 var, and this is just running different outer loops. It's the same data simulation window, so it's not the time here. So it's a different outer loops, and so we have 4 different trajectories or coupled models we are running, and here the importance is they're all based on the same land initial conditions. And then we run in parallel the SEKF, which is our land data simulation system essentially, and it's getting the screen level observations from this 2DOI. And then we produce analysis, but there is no exchange between the two systems within the same DA window. They only get for the next data simulation window, basically the new initial conditions, and then they run it over again. In the new setup, what we're doing is we have an outer loop coupling now. So the SEKF is running a coupled trajectory, or there's a possibility to activate the SEKF in a coupled trajectory together with the 40 var. And then here you see that we can update basically the consecutive outer loops with the new land feedback, the updated initial conditions. And also for the SEKF, we can run it basically with the updated atmospheric feedback. And though this is one of the example setups, but the idea is to try different configurations. And yeah, just coming to the main point here, what we were focusing on in the last year is having these infrastructure developments here in place for the SEKF as part of the 40 var outer loops to be flexible to run different configurations and finding an optimal degree of outer loop coupling. So the testing was about activating the SEKF as part of the first and later outer loops, and then also having these multiple 2DOIs, which generate the screen level observations based on consistent conditions in the SEKF, and having this feedback with updated land surface variables into the atmosphere and from the atmospheric fields to the land. And I'm going to show you some results over experiments which are 3 months, which are carried out along a 3-month period over the boreal winter. And the control one is our current weakly coupled system, and 3 different experiments around which have a different kind of degree of coupling. So the first one has like the SEKF only activating the first outer loop, and then consecutively enabling more the SEKF also in more outer loops. And the first results I wanted to show you is about what is the impact on the atmospheric forecast. So here you see plots of the normalized differences of the root mean square forecast error between the experiment and our control. So it's a percentage here, and that means the 0 line is the control experiment, and everything in the negative numbers means a reduction of our forecast error, which is a good sign. So for the temperature at 850 hectopascal, you see especially here in the tropics that we get a reduction of about 1 to 2% in the different forecast days. So this is the forecast days here on the x-axis, and for 2 meter temperature we get even more reduction. And so the green one is the one with the least kind of strength of coupling, whereas the black one is the one with the highest coupling. And just zooming in here and looking at the maps, so you see here the maps here. In this case, the blue colors are improvements, so it's reduction of focus error, whereas the red ones are degradations. And you see that apart from the noisy ocean here, you see that really the improvements here over Central Africa, and this is a region where we don't have so many synoptic observations, so no in situ stations of 2 meter temperature relative humidity, and this is the clear benefit of what brings this feeding back or these updated atmospheric conditions for the land, because the atmosphere has seen also satellite data which has information especially in that region where we don't have the information yet, looking at the observations we so far go into our land system. So we have in this sparse area improvements, and this is kind of the benefit of feeding back this the atmosphere to the land and balancing it and feeding it then even again back to the atmosphere. So looking at observations, so when we look at observations here, these are basically our background, or our background minus the observations. And we everything which is on the left hand side, so the 100% is the control, and everything which is on the goes towards the left is basically a reduction of forecast error. And we see that so it's also nicely fitting the observations, and especially here when you look at the synoptic observations here, we get a reduction in background departures. And we can also have a look at the maps, so to see how consistent it is globally. And there you see mostly blue color is again a reduction, and then we have some areas where we have some red colors here. So red means degradation, which is mostly over Northern Africa, but overall it's improving the atmosphere. So this is the main message here, like it's the observation like it, and it's improving the atmosphere, and a part of an increase of this kind of first gas departures over Northern Africa. And then So having a look now at the very lowest level of the atmosphere, which is the skin temperature, and also looking at the forecast error. So we looked at the 2-minute temperature and the temperature at a lower level in the atmosphere. But looking at the skin temperature, we see in the first couple of forecast days some increase in, this is again the normalized differences in root mean square forecast error, and so this something we would like to find out why. And so if we look at the maps, so here again, looking at the maps of skin temperature here for the first basically forecast step, which is the 12-hour here. So the one with the most degradations, and we see that the degradations really are focused here in areas northern Africa and also the Arabian Peninsula, and this makes us think like, okay, this is areas where we have a high fraction of bare soil. So looking here at percentage of bare soil is quite high here, and so this is most of the degradations are in areas where we have no vegetation here, and so this basically gave us to think like, okay, let's have a look at the real observations here. So so if the signal is a true signal in our validation, so looking at another set of independent observations, which are, so we look at where we compare the skin temperature with severe land surface temperature maps. And so what you can see here is the control, so our weakly coupled system still. And you see in the first picture here the diurnal cycle of the severe satellite land surface temperature product, and the diurnal cycle of our skin temperature. So they look similar, but somehow are not in the same magnitude. So what you see here, that if you look at the differences on the right-hand side, that the blue ones means reduction of diurnal cycle. So already in our control experiments, we have reduced diurnal cycle of about 10 Kelvin here. So looking for the difference between, let's say, high noon and midnight, so the 12 minus the 0 UTC analysis time. And now, also, apart from the diurnal cycle here, looking at the root mean square differences between the observations LST and our skin temperature forecast, you see that the kind of at the combined over the 3-month period, the combined reduction is quite big. So we have like up to 5 Kelvin here, basically increase in forecast error. But looking at the diurnal differences now, really we see that at 0 UTC, the forecast error is actually not that high over Africa, where we have the most degradations. But looking at the 12 UTC, we see a big, like the largest part of our forecast error. So, so now looking at the diurnal cycle again, so this was the control. So the control already showed an underestimated diurnal cycle. And now what happens when we increase now our the degree of coupling? So the first experiment with the lowest degree of coupling here, you see here. So here we have actually not so much of a reduction in diurnal cycle. So this is the experiment minus the control. So it's on top of the one which is already underestimated. And then the differences here, the differential root mean square error also against our control, which are both kind of compared to the severe LST. So here we don't have an increase in forecast errors, a decrease. So the blue color is good, the red color is bad. And now when we increase now the degree of coupling in the other experiments, we see that on the top, which is the diurnal cycle, is reducing even more, quite severely in some regions, and the forecast error is also going up. So here the positive forecast error, and which goes basically hand in hand with the reduction of the diurnal cycle. So now, having this in mind, and what I was just saying before, that we had most of the regions are in over bare soil areas where we have hardly vegetation, that made us try to optimize skin thermal conductivity of bare soil. So basically, when we update the land, so especially the uppermost level of the soil temperature, we have a coupling between that soil temperature and the skin temperature. And if this coupling is too high, we basically reduce the diurnal cycle of the skin temperature. So the idea here was to reduce the thermal conductivity. And what you see here is a new experiment which is comparing the configuration with the highest coupling. So it's the one I was showing here on the right, the highest coupling, and the one where I'm reducing the skin thermal conductivity over bare soils. So here you see this is separated by analysis time, and you see on the left-hand side, so when we reduce the skin thermal conductivity, this is the change in the mean skin temperature forecast field. Then we reduce basically our temperature, our skin temperature at nighttime, and we increase our skin temperature at daytime, which means that we kind of we extend our magnitude again, which is exactly what we wanted. So in these regions where we had the problems, a reduction of the skin thermal conductivity is alleviating this reduction of the diurnal cycle. So and also looking at atmospheric scores, and there you can see for the temperature at the lowest level, we have this, when we reduce the skin thermal conductivity, we have a positive impact over the latitudes around 30 degrees, which are exactly the areas over Africa here. And when we look at the synop observations also between the two experiments, we see that our new experiment gets a reduced first gas departure, which is exactly what we want. And then again, looking at our maps here for the synop observations, you see here we get a lot of blue over Northern Africa and Australia. So which is what we thought would happen. Then I want to go a step further. So when we have this outer loop coupling configurations in place and finding the best degree of coupling, we are able to exploit interface observations. So at ASIMWF, Sébastien, Massart, and others have developed this extended control vector 2D framework, which is essentially when you have an observations like in the microwave spectrum or in the infrared, we filter out usually the information which is not sensitive to the atmosphere in the 40 var. But when we know that we have some information content also for the land, we can enable another extended control or another variable. So we extend the state of our atmosphere by another variable, which is basically for example, the soil temperature, skin temperature in the land. So the idea is to have a new sync term that we, rather than filtering out this information, we add another variables which we basically change in the 40 var, which then kind of contains the information from the remaining information from the satellite, which is not sensitive to the atmosphere. So basically the control vector is extended by a new 2D field called the XCV, and here you see an example map of how does an increment look like in 40 var, which can then be assimilated in an outer loop coupled setup into the SEKF as an observation similar as our screen level observations at the moment. So this framework is used for a selected number of variables, having this new sync variable in place, and I just have here a preliminary assessment, really just using the information coming from one outer loop and using it as observations in the SEKF gives us, without having it tuned yet, so this is a very kind of recent figure, but we see that we get some benefits again in areas where we don't have information of the synop system, and and having some, for the blue is improvements again, some benefit from this new framework. And lastly, I was focusing here to give a summary on the development and investigation of the outer loop land atmosphere coupling, and the main message is here that the atmosphere likes it. So we have a positive impact for the temperature, especially here, but we also saw some degradation. So we cannot increase the coupling even more and more. We have to investigate when we get some degradations what is going on, And this is was kind of a nice example of a parameter estimation and how we can estimate a model parameter using our data assimilation system. And yeah, and as future work, yeah, evaluating also the surface heat fluxes when the coupling is changed, that we have the balanced initial conditions we want to have. And yeah, and the main focus in the future will be on this exploitations of interface observation. So once we have the absolute coupling fully in place, we can exploit more observations which are sensitive to both system components. And yeah, with that, I'm stopping here. I'm very happy to receive questions. Thank you very much.
Thank you, Christoph, for the great presentation. And I already see one question from Pat from Lars Neger. So he's wondering, extended common filters usually means that a linearized error integration is performed. So how is this done in your case? Because you mentioned that covariances are built from an ensemble.
Yeah, so we have, thanks for the question. So we use as our sensitivity, so in the Kalman gain basically is based on the background and the observation error covariance matrix and on the Jacobians. So the Jacobians essentially have the information of the EDA spread. So we use, for example, in order to update soil moisture, we would run our coupled model and have our sensitivities or our Jacobians computed from the 50 members we are running, and so the spread in our 2-meter temperature and the soil moisture, and we kind of it's basically a division of the covariances between these two variables and the variance of the respective control variable, such as soil moisture. So this is what we're doing, and this is for all the variables basically done.
Yeah. Okay, from you, Pat, I didn't see any further questions, and I think given the time, we should move forward. And if you have any further questions, please write them on Pad, and I think Christoph can write the answers afterwards. So now I will hand over my microphone.